Let's talk about half-life. So we'll define what half-life is, talk about what the equation is for half-life and how you use it and what the different variables mean in that equation, and then go through 2 different examples of half-life in radioactive decay and half-life in drug elimination. And through the different parts of these 2 examples, you'll kind of see every possible question that could be asked about half-life that you'd see in an algebra course or a pre-calc course or whatever. So let's do it. Half-life is defined as the time it takes for a substance to reduce to half of its original amount. And this is what the equation that correlates to half-life looks like. So you can see that this is an exponential decay equation with a rate of 1/2. So if we go through and define what each of these things mean, N naught is going to be our initial amount, right? So this is the initial amount of substance that we have. We're decaying at a rate of 1/2. Our T sub 1/2 is going to be our half-life of our substance. Our T is going to be our time elapsed. So this is going to be the independent variable, the input of our function. And then N of T is going to be the output of our function, so the amount of substance that we have at a certain time T. All right, given that information, let's try our first problem on radioactive decay. So it focuses around plutonium-241, which has a half-life of 14.4 years. So the first question says, if I start with 100 grams of this plutonium-241, how much will I have after 30 years? So if we come back up to our equation, our initial amount is 100 grams, so that's going to be where our N naught is. And then we want to know how much we're going to have after 30 years. So that's going to be the input to our function. And then our half-life is 14.4. So this is just a matter of putting an input into our function and figuring out what the output is. And then if I chuck that right side into a calculator, I'm going to get about 23.597 grams. All right, the next question asks us how many half-lives will occur in 25 years. So what we can do to figure this out is actually think about this exponent up here. So T, the amount of time that's elapsed, so 25 years, divided by our half-life is going to tell us how many half-lives have passed. So this gives you a little bit of context as to what's happening and why our exponent is important in this equation. It's how many half-lives have passed. All right, so if we have 25 years and our half-life of that plutonium-241 is 14.4 years, we're going to divide those 2 and we will get about 1.736 half-lives have occurred. So the next one gets a little bit spicier. It says, if a nuclear bomb was released with 10 kilograms of plutonium-241, how many years will pass until the amount is reduced to 1 kilogram? Right, so this 1 kilogram is our output, right? After a certain amount of time, it's reduced to 1 kilogram. Our initial amount this time is 10 kilograms, and our half-life is still 14.4, but this time we want to figure out what our T is, how much time it takes to go from 10 kilograms to 1 kilogram with plutonium-241. So if we plug all of that in, this is the equation that we want to try and solve for T. Right, so according to our algebraic rules, why don't we divide by 10 on both sides? So that's going to give me 0.1 is equal to 1/2 to the T over 14.4. This is where things get kind of sketchy, right? Because there's no amount of adding, subtracting, dividing, or multiplying that I can do to get the T by itself. And so the trick that we're going to use to isolate this T is to take advantage of logarithm properties. So what I'm going to do is natural log both sides, right? Ln is just log base E. But when I'm logging both sides, I can use whatever base that I want. So I could use log base 10, I could use log base 1/2, I could use log base E, whatever base I want to choose, as long as it's the same on both sides. Then, once we've logged both sides, this allows us to use that power rule. So we can take this power and turn it into a coefficient. Now it becomes a lot simpler to solve for T, right? We need to multiply by 14.4 on both sides and divide by ln of 1/2 on both sides, and we'll have it. That's going to give me 47.84 years. So it's going to take that many years for 10 kilograms of plutonium to reduce down to 1 kilogram. Let's try these half-life drug elimination problems. The first one says an adult took 25 milligrams of Benadryl. After 8 hours, 13.5 milligrams of Benadryl was left in the body. What is the half-life of Benadryl? Okay, so this time they give us an initial amount of Benadryl taken, a final amount of Benadryl taken after a certain amount of time, and we want to know what the half-life is. So this is going to be similar to the problem that we just did because we're trying to solve for a variable in the exponent. So let's first divide by 25 on both sides. We'll take the natural logarithm on both sides, or whatever logarithm your heart desires, and then we'll pull down that exponent. And now, how about we multiply by our half-life on both sides, and then divide by this ln quantity on both sides. That's going to give us that t 1/2 is equal to 8 times ln of 1/2 over ln of that 13.5 over 25, and we chuck that in a calculator. That's going to give us a half-life of approximately 9 hours. The next question says, how long until 95% of Benadryl is eliminated from the body? So we could use that initial amount we were provided in the first part that was 25 milligrams, but we can actually generalize this to whatever initial amount you could possibly give me. Because if we come back to our original equation, if we divide by n naught on both sides, that left side is going to give us the percentage of the drug left in our body, right? And so if we want to figure out how long until 95% of Benadryl is eliminated from the body, we're going to take 0.055% left is equal to the rest of our equation. We want to know when there's 5% left of Benadryl in the body, and this is going to be equal to 1/2 to the power of t over the half-life that we just solved for, 9 hours. Now our job is to solve for t. So because Benadryl has a half-life of 9 hours, no matter how much you initially put in, after 38.8 hours, we're going to have 5% left in the body, or 95% of Benadryl eliminated from the body. All right, so for our last problem, it says if a patient was found to have 19.84 milligrams of Benadryl in their body 12 hours after they claimed to take a pill, so 19.84, 12 hours, half-life, what was the initial dose? So this time we're solving for n naught. And because the variable that we're solving for is not in our exponent, this is just going to take some simple dividing by this whole thing on both sides. So the patient will have initially taken a dose of about 50 milligrams. All right, that was our last problem. You can see throughout these problems that we pretty much solved for every part of a half-life equation, except for the rate, of course. But these are a lot of the questions that you'll encounter when you're dealing with half-life, which comes up a lot in math classes because it introduces this idea of using logarithms in real life. So, thanks for watching all the way through. If this video was helpful to you, consider dropping a like, a comment, a concern, a constructive criticism. Consider sharing this with a family member, a friend, a distant acquaintance, all of the above. It super helps me out. But thanks for being here. Trying to be super active on YouTube and TikTok, so make sure to follow me on all those places. And Instagram too. So that's it.